Okay, we're going to give this a shot. Hi guys, it's Dr. Morgan. Welcome to Astronomy. I want to start with a overview of the universe and the scope of the universe as we know it. And I also want to talk with just a little bit of vocabulary that we have to make really, really sure that we use correctly in an astronomy class. Because sometimes when in casual conversation we use some of these words to talk about the universe, we mix up our scales. So the first thing I want to talk about is just these words. What are the main questions we want to talk about today? First, to talk about the relevant vocabulary for talking about astronomy, and then second, to talk about the distance scales, the relevant distance scales in modern contemporary astronomy. How big is stuff, how far away is stuff, etc. In order to do that, we're going to need to understand some units of measurement and things like that. One of the first things we want to make sure we are clear about is the distinction between these three terms: solar system, galaxy, and universe. We need to be very clear not to mix them up because they differ from one another by scales of millions, if not billions, in size. When we use the word universe or cosmos, we can use them interchangeably. We are talking about everything. This is a very famous picture from the history of astronomy. It was one of the earliest photographs from the Hubble Space Telescope deep field camera. Everything you see in this picture essentially is a galaxy. Even the smallest, dimmest little smudges of light in this image are galaxies. And our universe contains something like 100 billion galaxies, or a few 100 billion galaxies. We don't know this number precisely because, first of all, we don't count 1, 2, 3, 4, 5 up to 100 billion. The way we determine how many galaxies are in the universe is we take a representative sample of the sky and we count how many galaxies are in that sample, and we multiply that by the whole sky. By the way, the amount of sky that this photograph covers, and there are about 1,000 galaxies in this photograph, is about the same if you take your pinky finger and hold it up against the sky. That square covered by your fingernail on your pinky finger is about how big of a chunk of the sky the Hubble Space Telescope is photographing here. So every one of these little smudges of light is a galaxy. And a galaxy is a bunch of stars orbiting around their own common center of mass. And some galaxies can themselves have hundreds of billions of stars. So our universe contains about 100 billion galaxies. A galaxy contains a few 100 billion stars, which means there's 100 billion times 100 billion. That's a lot of zeros, stars in the universe. And we can see how scientists deal with those big numbers in mathematics in a little bit. This is a picture of a galaxy, a typical spiral galaxy, very much like our own Milky Way galaxy. It is not a picture of the Milky Way galaxy. We can't take a picture of the Milky Way galaxy because we live inside of it. This is actually a picture of the Andromeda galaxy, one of the closest big spiral galaxies to us. A typical galaxy contains hundreds of billions of stars, up to maybe even 1 trillion stars for a large galaxy. Our own Milky Way galaxy contains 200 or 300 billion stars. So when we use the word galaxy, we're referring to one of these spiral or elliptical orbiting blobs of hundreds of billions of stars. We live in a galaxy, the Milky Way. This is the Andromeda galaxy, about 2 million light years away from us. You can actually see the Andromeda galaxy with your naked eye. If you go someplace very, very, very dark and know where to look for it, you can see the little smudge of light in the sky. That is the Andromeda galaxy. And there are hundreds of billions of these. Our galaxy is gravitationally bound to the Andromeda galaxy. Our galaxy and Andromeda are part of what's called the local group of galaxies. The distance between our Milky Way and Andromeda is about 2 million light years. And there are a few dozen other smaller galaxies in the local group. Milky Way and Andromeda are the two biggest galaxies in the local group, but there are dozens of others. The fact that the Andromeda galaxy is 2 million light years away Means that the meaning of a light year is that's the distance that light travels in a year. That means that the light that is reaching us now from the Andromeda Galaxy left the Andromeda Galaxy 2 million years ago. This is an interesting fact about astronomy. Because light travels at a finite speed and because things in space are very, very far away from us, we are, as we look at further and further and further objects in the universe, looking further and further and further back in time. Much like as a geologist digs deeper and deeper and deeper and deeper into the sediments of the Earth, they are looking at earlier and earlier and earlier eras in the Earth's geological history. As astronomers look further and further and further out into the universe, they are learning about things that were going on in the universe further and further and further back in time. The Hubble Space Telescope has been around since I was a freshman in college, taking the same class you are taking right now. So it is getting kind of old, and we recently launched a improvement called the James Webb Space Telescope. One of your assignments early on in the course is going to be to do a little research and to answer the question of what exactly is the James Webb Space Telescope and how is it different from the Hubble. But if you ask why scientists are always wanting to build these bigger and bigger and bigger telescopes, it's not just to get better magnified pictures of the things we can already see, although that's part of it. It's to look at things that are dimmer and dimmer and dimmer because they are further and further and further away. By looking at things that are very, very far away, we are learning not just about far away things in the universe, but we are learning about what happened in the universe 1 million years ago, 1 billion years ago, 5 billion years ago, 10 billion years ago, all the way back to the time of the Big Bang, about 13.5 billion years ago. So I'm tossing around this word light year. Light year is a unit of distance, not a unit of time. Because distances in space are so big, it's ridiculous to talk about them in terms of miles or kilometers or everyday units that we use to describe distances on the Earth. So we use the speed of light as a sort of measuring stick or measuring standard for talking about distances in space. For example, light takes 2 seconds to go from the Earth to the moon, or the moon to the Earth. We could say that the moon is around 2 light seconds from the Earth. Light takes about 8 minutes to go from the sun to the Earth. So we could say the sun is about 8 light minutes away from the sun. This is using a time and a speed to talk about a distance. This may seem strange until you realize we do this in everyday conversation all the time. If I ask, how far away do you live from work? You might say, oh, it's about a 10-minute drive. Right? That's not a distance, that's a time and a speed. Right? How far away is the grocery store? It's about a 15-minute walk. Right? It's 15 walk minutes away from your house. This is no different. It's using the speed of some standard. We could use a car, or how fast a person walks, or, in this case, the speed of light, and an amount of time. So the distance that light travels in a year is a huge distance. It is more than 6 trillion miles. I don't know the exact number. I don't have it stored in my head. But you can think of a light year as 6 trillion miles. That's a lot of zeros, right? A trillion is a million, 12 zeros. So the distance to nearby stars is 4, 10, 20, 100 light years. That means when we look at the stars we see in the sky at night, the light left those stars 4 years ago, 20 years ago, 100 years ago. There aren't too many stars in the sky that you can see with your eye that are more than a couple hundred light years away. But when we look at distant galaxies that we can only see in the telescope, they might be 1 million light years away, or 1 billion light years away, or 10 billion light years away. Okay, so a light year is a very big distance unit that we use to measure very big distances between stars and between galaxies in space. So, the stars that we can see in the sky, when we go out at night, go someplace dark, look up in the sky, we see a bunch of stars. Those stars are between tens of light years away, up to maybe the dimmest stars you see in the sky might be 1,000 light years away. The nearest galaxies, like Andromeda and the other galaxies in our local group, are millions of light years away. The distant galaxies that we can only see in our most powerful telescopes and show up as tiny, tiny specks, even in the Hubble, are billions of light years away. So the scale of our universe within galaxies is thousands of light years. Between galaxies is millions of light years. And the universe as a whole, the distance scale is billions of light years. Okay? This is a picture of our own Milky Way galaxy. It doesn't look much like the picture of the Andromeda because we are inside of it. The galaxy is all around us. When we look in any direction in space, we see our galaxy, and there is stuff in the galaxy. All these black clouds are not places where there's no stars. There's places where there's gas and dust in the galaxy blocking our view of the rest of the galaxy. But we live inside of a galaxy, and our own Milky Way contains 200, 300, 400 billion stars. We're not sure exactly how many because there's stuff in our galaxy that's in our way. We can't see it all. Our sun is not at the center of our galaxy. Our sun is located a little more than halfway out from the center to one edge, something like, I think 20 or 25,000 light years away from the center. When we look at the stars in our own galaxy, we notice something important, interesting, noteworthy, and they're all different. They're different brightnesses. We look up at the sky at night, we see stars that are dim, stars that are bright. They are different colors. We see reddish ones and yellowish ones and bluish ones. And that probably means something. And the question is, what does that mean? We'll talk about that next week. It also raises a question of, when we look up at the sky and we see a bright star and a dim star, is that bright star really brighter than the dim star? Or is the bright star just close and the dim star far away? How can we tell how bright things are in space if we don't know how far away they are? And how can we tell how far away they are if we don't know how bright they are? It turns out that knowing the actual distance and brightness of things in space is really, really hard. It's one of the hardest puzzles in astronomy, is to figure out how far away things are. We'll talk about some of the tools we have for doing that. Again, fairly early on in the class, probably in the second week of the course. So we talked about universe and cosmos, which mean everything. Galaxy, which means one of these orbiting blobs of stars, several hundred billions of stars all orbiting one another, like our Milky Way, like Andromeda. The last word we have to make sure to be careful to use correctly is solar system. When we talk about the word solar, when we use the word solar system, we are talking about just our sun, our 8 or 9 planets. Let's not get into a fight now about whether Pluto is a planet. We'll talk about that later. And all the other stuff in orbit around our sun. If we're being nitpicky about the word solar system, we should only use the word solar system to talk about our sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, all the comets and asteroids orbiting our sun. We should not ever talk about other solar systems. There are no other solar systems because solar refers to our sun. I might slip up every once in a while and talk about other solar systems. What we should say if we're talking about other stars and their planets, we should call those planetary systems. Okay, so there are other planetary systems. Our planetary system is called the solar system. And our solar system includes not just the planets and their moons, but all of the stuff orbiting the sun. When talking about distances inside the solar system, it's not so big that we need light years. Our solar system is a fraction of a light year across. We need a new distance yardstick for talking about the solar system. For example, the Earth is 93 million miles from the sun, and that's a really, really big number. And if we don't want to be tossing around really big numbers, we just define a new unit. And the unit of measurement we use is the distance from the Earth to the sun, which we call an astronomical unit. So an astronomical unit is 93 million miles. Our Earth is 1 astronomical unit on average, because it changes a little bit. Like the Earth's orbit's not a perfect circle, right? Sometimes it's a little closer, sometimes it's a little further. The average is about 93 million miles. That distance, the average distance from the Earth to the Sun, is 1 AU, 1 astronomical unit. And so for expressing distances inside of our solar system, between the Earth and Jupiter, or Jupiter and Saturn, between the Sun and Pluto, the convenient unit of distance to use is not the light year, it is the astronomical unit. Here is a cartoon picture of our solar system. Obviously the planets are not to scale, they're to scale to one another, but they're not to scale to the distances between them, obviously. The distance from the Sun to the Earth is 1 AU. The distance from the Sun to Venus is about 70% that, 0.7 AU. The distance from the Sun to Mercury is about 0.4 astronomical units. So Mercury is a little less than half the distance from the Earth to the Sun. The distance to Mars from the Sun is 1.5 AU, which means sometimes the Earth is half an AU from Mars, and sometimes it's 2.5 AUs from Mars, when they're on the same side or the opposite side of the Sun. Jupiter is about 5 astronomical units from the Sun, and Saturn's a little less than 10, about 9.5. Uranus and Neptune, respectively, are 19 and I think 30. I've got to look at the presentation to make sure I get the numbers right. Uranus is about 19 AU from the Sun. Neptune is about 30. Notice that's way further. The planets get further apart from one another as you go further out in the solar system. And then Pluto actually comes in closer to the Sun than Neptune sometimes, a little less than 30 AU. But when it's at its furthest part from the Sun, it's about 50 AUs from the Sun. Pluto's orbit is very oval, very elliptical. It's not always the same distance, even close to the same distance from the Sun. We'll talk about all this stuff when we talk about orbits in general, and we talk about the relationship between orbits and gravity. So that's the planets. The planets have moons. We have 1 moon. Mars has 2 moons. Jupiter and Saturn have 60-some moons. I stopped counting back in the 90s. It's too many to keep track of. Uranus and Neptune have a few dozen moons. Pluto's got 1 big moon and 2 or 3 little tiny moons. Those moons are all part of our solar system. The planets go around the Sun, the moons go around the planets. That's our solar system. But that's not all that our solar system is. Our solar system is filled with comets and asteroids. Those are part of our solar system. They orbit the Sun just like the planets orbit the Sun. If you go out beyond the orbit of Pluto, there is still stuff that orbits the Sun. Pluto is not the edge of our solar system. The solar system does not stop at Pluto. In fact, there's a whole orbiting ring of stuff out beyond the orbit of Pluto. Or you could actually say that the orbit of Pluto is the inner edge of this thing called the Kuiper Belt. One of the reasons we don't consider Pluto to be a planet anymore, technically, is that Pluto's orbit takes it out to the edge of the Kuiper Belt. And the Kuiper Belt is filled with other objects that are kind of like Pluto. Sedna and Eris and Quaoar, and we'll talk about these trans-Neptunian objects, these large Kuiper Belt objects, or dwarf planets that live at the edge of the solar system, when we talk about the solar system in great detail. The point is, there's a bunch of stuff outside the orbit of Pluto that's as big as small planets like Pluto. That's the size of a house, or the size of a car, or the size of gravel in your driveway, or the size of a grain of sand. All of this stuff orbiting the Sun in this diffuse belt called the Kuiper Belt. The size of the Kuiper Belt is about the size of Pluto's orbit. That shouldn't be 50 AU in diameter. That should be 50 AU in radius, actually. If you go out beyond the Kuiper Belt, there's still more stuff orbiting the Sun. If you go out beyond the Kuiper Belt, there's things the size of snowflakes and grains of dust and little bits of mineral grains, all orbiting the Sun. It might take them 10,000 years to go around the Sun one time. This is called the Oort cloud. The Oort cloud is a diffuse halo of stuff that you can think of as just being leftover junk from the formation of the solar system. It's little grains of sand and ice and dust and gas that was moving too fast to be pulled into the solar system when the solar system formed, but it is still out there orbiting the sun, and it might be tens of thousands of AU across. We're actually not sure what the extent of the Oort cloud is because we've never sent any spaceships out that far, except maybe Voyager 1 and 2. Are they out of the Oort cloud yet? I don't think they are. But the Oort cloud is so diffuse, the particles are so tiny and far apart, you can't see them. It's just like the fact that between you and your computer screen right now, there's dust grains floating in the air, and you can't see those dust grains because they're tiny and all the other stuff around you is too bright, but they are there. So the solar system includes planets, moons, comets and asteroids, all the leftover junk and debris that orbits the sun, and some of that is actually very, very far away from the sun. You're not out of the solar system until you reach the point where the gas and dust that you encounter in interstellar space is no longer bound by the sun's gravity. You're in interstellar space when you're so far away that the things are no longer orbiting the sun, and then when you get to another star, you become part of that star's planetary system, not solar system. Okay, so that is just all mostly vocabulary about distance units, light years and astronomical units, super important, about how to use the words universe, galaxy, solar system properly, and just to get a sense of the scales involved when thinking about our modern picture of the universe. Again, if we're inside of our solar system, we're talking about tens of astronomical units. If we're inside our galaxy, we're talking about thousands of light years. If we're talking about between galaxies, we're talking about millions of light years. If we're talking about cosmic distance scales of the universe as a whole, we are then talking about billions of light years across.